Right, guys. Last lesson. I just wanted to go over and recap with some more concise notes from what all those recordings I sent last time. So, in this, you will see some additional points from what I discussed last session. So, ideal gases. There are three gas laws. Um, First one I'm going to discuss is Boyle's law. Um, Remember, throughout this, they are gases, not liquids. They are not. There's no changes of state into any of the liquids or solids. Okay, so it's how gases behave at different temperatures, different pressures, how their volume changes accordingly. Okay, so Boyle's law. Um, the relationship that we have. Is an inverse proportional relation where the pressure is inversely proportional to the volume when uh, the gas is held at a constant mass. That means the number of particles inside that container, or where the gas is within, does not change. And the temperature, the overall temperature, as the pressure is increasing, does not change either. Another word, that word often you may see to um, which is the same as the constant temperature, is isothermal. And that means the temperature remains the same. Now, that means that the pressure times the volume is equal to a constant. So if I take a pressure here, multiply by volume over there, it will be the same value as the pressure over here, multiply by volume over here. Now, if I have the same constant, then what I can say is the pressure times the volume before is equal to the pressure times the volume after. And sometimes questions go down the route of the pressure increase, what will happen to the volume? And you could use this expression. You only use this when there's a constant temperature and a constant mass of gas. Charles's law. You have got the pressure directly proportional to the temperature. This is the absolute temperature. The thermodynamic temperature often is referred to as well. And it's measured in Kelvin, and it scales back all the way to zero. And at zero Kelvin, and the volume of the gas is zero. Quite difficult to imagine, but um, we won't dwell on that too much. So as the temperature increases, the volume of the gas increases. Again, you've got the constant number of particles in this system, and the pressure throughout the increase in temperature is constant. And what happens is the volume will increase as a result of increasing the temperature if the pressure is to remain the same. For every 1 degree increase is the same as 1 degree Kelvin increase, so the increments are exactly the same. And to convert from degrees Celsius to Kelvin, you just add 273, and 0 Kelvin is actually the same as minus 273 degrees Celsius. Now, if I did the same experiment, but I plotted temperature in Celsius, what I would have found is at 0 degrees, I would have seen the gas would have been at a certain volume. And if I continue to reduce the temperature, I would have to go all the way down to minus 273 degrees for the volume to become tiny and negligible. Okay, which is why we use the Kelvin scale instead. That is a better way of describing the relationship between volume and temperature. Now, the pressure law, the Gay-Lussac law, is where the pressure is directly proportional to the thermodynamic temperature in Kelvin. Here again, we've got the constant number of particles in the system, but the volume is held constant. So we're not allowing the volume to change as the temperature increases. As a result, the pressure will increase. 0 Kelvin is known as absolute zero. I should have mentioned that before. And here, at 0 Kelvin, we've got zero volume, as we've seen here. Also, at that point, the kinetic energy of the particles is equal to zero, and the potential energy is equal to zero. Difficult concept. Everything stands still, but at zero volume, because we've said the ideal gases, the particles, take no volume. So then, if we say something's an ideal gas, then it is possible, but in reality, that's not the case. And considering that the volume is constant, we can look at the pressure over the temperature, i.e., the gradient is constant throughout. So that is a gradient. So if pressure changes, we can figure out what the new temperature would be for a system like this with this expression. Now, we looked at last lesson equations of state. You could write it with pressure times volume is the number of moles times by the molar gas constant times by the absolute temperature, or pressure times volume is equal to the number of particles times by the Boltzmann constant times by the absolute temperature. So either or. As you see, both of them are equal to PV. And you got T there. So what I've done is I've rearranged it to get PV over T is equal to NR, and PV over T is equal to NK. And we see that NR is equal to NK because they're both equal to PV over T. And K, the Boltzmann constant, is equal to the number of moles times by the molar gas constant divided by the number of particles. The number of moles divided by the number of particles is actually 1 over the Avogadro's constant, and that's the number of moles, and that's the number of particles divided by the Avogadro's constant, which is 6.02 times 10 to the 23. So Boltzmann constant, it is a constant referring to a single particle because we've divided the molar gas constant by 6.02 times 10 to the 23 particles. So this constant refers to single particles rather than a mole of particles. Okay, which is better in descriptions, and I think we use the Boltzmann constant a lot more rather than the molar gas constant in physics. So in scenarios where P, V, and T are all variables, so where we've got a system where the pressure, volume, or temperature can change, and the number of particles in that system is fixed, we can say that P1 times V1 over T1 is equal to P2 times V2 over T2. So this could be a before scenario, this could be an after scenario. So something in the system changes and we want to work out something afterwards. This is the before and this is the after. Okay. And finally, we looked at the ideal gas properties or the kinetic theory of gases assumptions. So they're the same thing. So the assumptions to do with the kinetic theory of gases or what are the ideal gas properties refer to the same thing. So the particles are moving randomly. That's Brownian motion, where Einstein did his experiment and looked at the particles moving in all into different random directions. There are no attractions between the particles, and there's no loss of energy when the particles collide with each other. That's this elastic collision section. The volume of particles, we're considering that these particles are negligible volume, and the duration of collision against a surface is tiny compared to the time between successive collisions. So what we are looking at is the frequency of collisions defines pressure rather than the time of the collision between on a surface. So we will look at that when we're looking at kinetic theory of gases. So that was last lesson. Okay. The next video, I'm going to look at the kinetic theory of gases.